Hi, in this video we are going to be talking about Unreal's material system. Unreal, like most other modern real-time rendering engines, uses a physically based material and rendering system. Before you watch any further, open up the documentation on the physically based material system and read through it. This is a nice and concise overview of how the system works. If you want to get more in depth, also check out the references at the end of this page. Now that you have gone through the basics, download the base project from here and launch it once you have done so. Once you have loaded up the project, feel free to check out what's in the level. This is a pretty basic setup that contains 4 of the material preview meshes that you will need to apply the materials to. Going over the contents of the project, you should mostly care about 2 folders, the materials folder that is currently empty, and the textures folder that contains all of the textures that you will need to recreate the 4 materials specified in the task. If you do want to check out the other materials that exist in the level, look in the Sun Temples Assets materials folder. These materials and material instances can actually be more complex than the ones that you will need to create, but can be good examples of the type of materials that can be used in production or in productions of such demo scenes. Now diving straight into the material system itself, let's go into the materials folder and create our own first material. For that, you can right click anywhere in the content folder here and pick material. This material is going to be for testing purposes mainly, so I'll be naming it in a way that reflects this. Now that we have created the material asset, double click it to open the material editor. Let's go over the components of the material editor. On the top here is the main toolbar. On the left side here is the preview window where we can see a real-time preview of the material, in the case that we do have the live preview option selected. Below that we have the details panel that shows us the details of the currently selected node, which currently is the master node. And the master node itself is in the main work area. On the right here I have the palette section that shows all the functions that are available to us. And in the bottom I have the material editor stats that can show the details of the material once it is compiled and errors if it fails to compile. Also on the left here is the parameters default values section. This will enable us to change the default values of the parameters that we will be adding to the material. If your material editor window looks different, check the Windows section in the main menu bar. You should find all the missing bits here. In this new material that we just created, there is this master node or the result node of the material. It has a bunch of inputs that can be modified by all the functions that are available for us. It itself also has parameters that we can change. You can access them if you don't have any node selected or if you select the results node. We can see the parameters in the details section here. The first option is to define the physical material. This will define how objects that have this material applied to them will interact in the world. In the materials section, we can define the high-level options for the material's looks. The material domain describes in which cases the materials will be used. By default, this is set to surface, as in the surface of geometry, but there are other options that also include domains that you might not think about, like for example, post-processing or user interfaces. The blend mode describes how the material will be blended. These options I would categorize into 2 main sections, opaque and masked materials. Opaque materials being fully opaque and non-see-through at all, and all the transparent options. The decal blending mode is only available if the material domain is set to be deferred decals. The shading model describes which shader is used. The default lit shader, the unlit shader that does not have any lighting information computed on it, and other shaders for more complex things like eyes and hair. Also looking at the main material node now, we can see that when the unlit shader is used, many of the parameters that were available previously are now grayed out and don't have any effect on the look of the material. And if we chose a more complex shader, for example one that supports subsurface scattering, we can see that we get an extra option corresponding to it, which in this case is the subsurface color. I will be resetting the shading model to the default lit option. The two-sided option toggles if the backface culling is turned on or off. All of the inputs in this results node can be combined into material attributes input. This can be useful when building layered materials. Let me reset the preview geometry to be the sphere, and let's start actually modifying our material here. Navigation in the graph view is similar to blueprints. Right-click and drag to move around. Scroll in and out to change the scale. Left-click to select and right-click to open the search menu. The first thing we are going to be changing is the base color of our material. This value is defined as a vector, so let's create the constant vector3. For that, we can search for it in the search menu by right-clicking or use a keyboard shortcut. The shortcut for creating a vector3 constant is holding down 3 and left-clicking anywhere in the graph. Looking at the node header here, we can see that the node is initialized to 000 or black. We can change its value in the details section by modifying individual components of it, or by using the color picker by double-clicking this rectangle here. We can change the hue and saturation by dragging around in the circle here. We can modify the saturation separately by dragging this slider up and down. And we can change the value by modifying this slider here. If you want to, you can also directly input the RGB values or the hex values. Let's click OK to save our changes. To use this constant as our base color, just connect it to the base color input. We can inspect the changes in the viewport here. If we wanted the changes to be applied to the objects that use this material in the world as well, we would need to click the apply button and save it for good measure. In fact, let's check it out in the level right now. Having navigated back to the level view, let's select an object that we can apply our material to. To apply the material, you can either left click and drag it on the object. This took a second to update because this material was not used on static meshes before. But looking at this object here, we can see that parts of the object are not using the material that we just created. And if we select the object, we can see that in the details section and in the material sub options, we can see that the second element is using a different material. So if we wanted to change this as well, we can drag the material on here from the content browser, or we can search for it in this drop down here. To reset the material of this element, click the reset to default option. Let's do some additional changes to our material. Looking at the metallic input, this controls the metalness of the look of the material and is a float value. So instead of creating a vector, let's create a float value. For that, hold down 1 and left click anywhere in the graph and connect this node's output to the metallic value input. Because the default value of the metallic input is 0, or the material should look like a dielectric or a non-metal, plugging in this 0 here did nothing to change the appearance of the material. So to see a change, let's modify the value here. This now looks quite a bit more like a metallic Christmas ornament. When talking about the materials that we encounter in our everyday life, most of them are either non-metals or dielectrics, meaning this value should be 0, or metals, in which case the value here should be 1. The in-between values would represent some sort of semiconductors, which are quite rare and thus we don't encounter them that often. So when creating your materials, it is a good idea to either pick 1 or 0 here. I would use the in-between values in instances where a metallic surface was covered with dust, for example. When it comes to metals, the base color values themselves are actually inferred from real-world physical properties, and there are lookup tables to see what these values should be. The values for some specific metals are actually brought out here. So if we wanted to recreate the look of gold, let's enter in these values in our material. Our material has a very sandblasted look. This is due to the roughness value. Let's change it to be smoother instead. For that, let's create another float constant. Let's enter in a low roughness value. And let's connect it to the roughness input. The roughness value goes between 0 and 1. 0 meaning that the surface is fully smooth, and 1 meaning that the surface is fully rough. So having the value of 0.1 here means that our golden surface is quite smooth. You can also think of roughness as microscale normals. If there is a lot of change in the normal direction, the material would be really rough, and if there's very little change, it would be really smooth. The default value for roughness is 0.5. The default value for specular is also 0.5, but this specular value behaves very differently from the one used in the Blinn Phong or Phong model. In here it actually defines the index of refraction of the material, and this 0.5 means that the index of refraction would be 1.5. Most non-metals have their index of refraction or IOR near 1.5. And if you don't know that the specific material that you're trying to create has a different value, then leave this at default. Also note that this value only affects non-metallic materials. The next input is emissive color. This defines if the material emits light or electromagnetic radiation in the visible spectrum. Note that most materials at room temperature do not. Just to see what this looks like, let's add in a non-zero value here. But this time let's use a color parameter, not a constant. The shortcut for adding a 4-vector constant is holding down V and left-clicking. Let's name it emissive and connect it. If we change this value from 0, we can see that our material will start to glow. Also note that the emissive color values are not clamped to 1, so we can actually go higher than that. And let's enter 100. Now you can see that we are actually starting to get bloom around our sphere. As this is a color, it doesn't have to be in grayscale, so we can also have colors. If the brightnesses are very high, then the saturation of the emissive color will be reduced. This behavior comes from the filmic tone mapper that is enabled by default. You can disable it by changing a console value, but in our case, as we want to have a realistic look, let's not do so. Next we have the normal input. This is also vector, noting the normal direction of the surface. By default this is in tangent space, and usually you don't want to modify this value uniformly. A good way of doing that is to sample a texture. So let's create a texture sample node. For that let's hold down T and left click. Right now we can see that no textures are selected. Let's pick one. Tangent space normal maps usually have a certain purple look to them. We could scroll through the whole list, but instead let's search for normal. I am going to be using the Space Tiles 1 normal map. Now let's connect it up. And looking at the viewport, we can see that our sphere now has a lot more detail on it, or perceived surface normal detail. How this texture is sampled on our object depends on the object's UV coordinates. You actually have direct access to them. To add the texture coordinate node, let's hold down U and left click. Let's connect its output to the UV input of the texture sample node. To increase the tiling of the texture, we can increase the U and V values here. Let's increase both to 4. Now we can see that the tiles are much smaller and the texture itself is repeated 4 times in both directions. If you wanted, you could actually take a look at the UV coordinates directly. For that, you can right click on the node and click the Start Preview node option. To get a better view, let's select the cube as our preview geometry. Observe the difference when I reset the U and V tiling values. Also note this green-red tonality of our preview here. As UV coordinates lay out our object in 2 dimensions or on a plane, we are not using the Z value or blue here. You can also preview any of the other nodes by doing the same action of right-clicking and using the Start Preview node option. And if we select our metallic option, we can also preview that as well. This is now in grayscale, and now our cube is white because our cube is fully metallic. You can do this for all your nodes. To disable this preview mode, right-click it again and click the Stop Previewing node option. Previously we added a constant as well as a parameter to our material. The neat thing about parameters is that they can be used in material instances as well as be changed during runtime. Having access to material instances is a very powerful tool. To create a new material instance, let's navigate back to our level editor view. Let's right-click on our material and choose the topmost Create Material Instance option. Let's leave the name as is. To open up our instance, let's double-click it. This view is very different from the default material editor view. We have a very large preview and the details section to the right. In the details section, we can see that our parent material is this m_testing_0. We can override some base material properties and change its light mass settings. But the most interesting for us is this parameters group. We can see the emissive parameter that we defined. If we tick this flag in front of it, we can now actually edit it. And now when I bring up the color picker and change the value, I can see the value change in real time. Because gold wouldn't glow this way, having this as a parameter is not that useful. But what would be really useful would be the ability to change the normal map if we wanted to. For that, let's go back into our master material. We could add in a new texture sample parameter node, but we can also right-click on our texture sample node and use the convert to parameter option. Let's name it something sensible. I'll be using text normal. Now let's save the material. This will take a second for the underlying shaders to compile. And let's go back to our instance now. We can see our new parameter here. Now by ticking this, we can override the value. We could select any of the textures here, but if we selected the texture that was not the normal map, we will get very strange results. Again, let's search for normal. And let's select the gold scuffed normal option. Let's save our material instance. Let's go back into a level editor view. And let's drag and drop this new material on top of our material preview mesh. Let's create a new instance of our parent material. Let's leave the name as is. Let's open it up. And let's also override the normal map of this material instance. I am going to be using the rusted iron normal map texture. Let's save this as well. And let's go back into our level editor view. Now I have 3 materials, each of which has a different normal map. But now instead of having to create a new base material, I only had to change one parameter to have many different looks. Now let's try and recreate the actual space tiles material. For that, I'll get rid of these nodes here. Let's create a new texture sampler and let's connect it to our base color input. I got an error that this texture sampler is missing the input texture, so let's select it. I'm going to be searching for spaced. I'm going to be using the albedo texture as this corresponds to the base color. I'm going to copy this with Ctrl+C and paste an instance with Ctrl+V. I'm going to change the texture to the roughness map. And I'm going to hook it up to the roughness input. But as roughness is only a float value, I'm not going to be plugging in the RGB value, but instead going to be using a single channel. As this texture is grayscale, it doesn't really matter which channel I use. So I'm picking red. To get a bit better of a view, let's change back to the sphere preview option. You should be able to see more of a highlight on the tiles themselves and less of it between the cracks. This now looks very much like the end result should. -1 detail. It is missing the displacement on the edges here. That can be done by using this world position offset option. Let's add in a texture sample and let's select the correct displacement map. This is space tiles 1 height. Although the world position offset is a vector input, let's use the red channel as the input texture is grayscale. Nothing much seemed to happen. This is due to all the values in the texture being less than 1 and the displacement amount itself being in centimeters. So let's multiply this value. For that, let's add in a multiplication node. Shortcut for this would be holding down M and left clicking. Let's wire it in by control clicking on this red output here and attaching it to the multiply output and connecting the red output into the multiply A's input. And let's actually change this B input to be a scalar parameter. To add a scalar parameter, hold down S and left click. Let's change the name to displacement amount. And let's change its default value to be something higher, for example, 50 for 50 centimeters. And let's hook it up. We can now see that our mesh is indeed being displaced, but this displacement is not happening in the correct direction. Right now we are inputting a scalar value into this world position offset, and it is interpreting this scalar value as a vector where all the channels are equal. So it is displacing it in the z, y and x axis equally. To overcome this, we actually need to do the displacement in the direction of the local normals. For that, let's add in another multiply node. Let's connect it up. For this second input, we want to use the vertex normals. We can see the vertex normal in worldspace option. Having added this in, now the displacement happens in the correct directions. This looks more or less good, but if we zoomed in, we could see that the quality of the displacement is not all that it could be. To get a better idea of this, let's actually choose the cube primitive as our preview mesh. And now, having zoomed out, we can see that this does not work at all. This happens because this world position offset is applied to the vertices that actually exist in the mesh. To show you a quick preview of this, I can enable wireframe mode. The shortcut for this is Alt+2. Because the cube has so little geometric detail, it is very hard to make it out in front of the sky sphere. But toggling back to the sphere, we can see that the sphere has a lot more detail in it. And thus, we can see the displacement map a lot better. But we can make our material also work on this simpler cube as well. For that, we need to enable tessellation. Let's deselect our vertex normal node and let's scroll down to the tessellation section here. We can see that no tessellation is enabled. We are going to be using the flat tessellation option. Having this enabled, the world displacement input was enabled. So to actually make our proper displacement appear, let's connect this input to that instead. Let's also enable crack-free displacement to get rid of these seams here. The previews passing out like this for me seems to be an issue with the current engine version. Let's go back to the sphere. To see the adaptive tessellation in action, let's go back into the wireframe mode with the shortcut Alt+2. And if you zoom in and out, you can see smaller triangles appear and disappear as you move the camera further and closer. Let's go back into shaded mode with Alt+4. The current displacement amount seems a bit too high, so I'll be decreasing this a little bit. This looks a bit better. I might also want to change the tiling of my material. For that, let's connect this texture coordinates node up to the other UV inputs. And let's actually make it a parameter. For that, let's multiply our texture coordinates with a set of new scalar parameters. Let's add in a multiply node. Let's wire it in. Let's add in new scalar parameters. Let's name them something sensible like U tiling and V tiling. And let's combine them into a vector 2 like the texture coordinates are. For that, we can use the append node. Actually, I wired them in the wrong way, because U should be the horizontal axis and V should be the vertical axis. Also, let's give these parameters more sensible default values. 1 in this case would be the default. Now let's save our material. And let's go back to our material instance. Let's untick the override normal texture option. And let's tick the U tiling override option. Now changing this value, I can see the change in tiling in the horizontal axis. I can do the same for the vertical one. This brings us to the end of this video. But before that, a few more pointers. You can override these other texture samples as new parameters. You might want to add some extra ones, for example the metallic channel, which was not needed for this material. I will be taking a close look at the plausibility of the materials that you create. For non-metals, you have a lot more free range when selecting the base color, but when it comes to metals, I will be expecting some very specific values here. Note that there might be textures that have those specific values in them. In some cases, you might want to use a texture parameter in one case and the vector parameter in another. To achieve that, you can use the static switch parameter. So if you want to use the base color texture in this example, let's enable the default value to be true, and let's connect the texture sample node to the true input. And let's add in a new parameter for the uniform color option. And let's connect this to the false input of our switch and the output of the switch into the base color option. Let's save our material. And now looking at the instance, if we override the use base color texture option, our material turns black because that is the color of the color parameter here. We can override that as well. And if we re-enable the use of the texture option instead, it gets its color back. This might be a really useful option for the metallic input. Also name your master material something sensible as well as the instances. But that is indeed it. Thank you for watching.